Hello there, and welcome back to Fall Asleep to Science Channel. Tonight we turn to the beginning of beginnings, to the mystery that stands before everything else. Before stars, before light, before even the fabric of space itself, there was nothing. Or perhaps something so different from what we call something that the word no longer fits. It is quiet here. No sound, no matter, no movement. No space to move through, no time to measure motion. Only a kind of potential still and undefined. Then in less than a heartbeat, the universe appears. Not as an explosion bursting outward, but as expansion itself, a sudden swelling of space from a single, unimaginably dense point. From that moment, time begins. Temperature, gravity, energy, matter, all awaken. We call this instant the Big Bang, a phrase that feels loud, though the truth is softer, stranger, more complete. It is not the sound of a blast, but the unfolding of reality. Every atom that will ever exist, every galaxy that will ever shine, begins here in that brief, dazzling birth. And yet, behind the brilliance of that moment, waits the deepest question of all. If the Big Bang created everything, time, space, energy, the laws of physics themselves, what caused the Big Bang? What came before the beginning? If before even means anything at all. Let your mind drift there for a moment, to the edge where language thins and imagination becomes silence, where nothing and everything touch. Before we wander further, I'd love to know, where in the world are you listening from tonight? A city washed in amber light, a quiet village beneath real stars, each tiny dot on the map, another soul looking up together. And if these calm explorations help your thoughts slow and soften, a gentle like or a quiet tap on subscribe helps this little corner of the cosmos reach others who might need it too. One sleepy traveler at a time. For now, breathe easily as the night deepens around you. The universe expands softly, and even its first question unfolds in calmness. The moment we call the beginning is not a single flash in time, but a gentle unfolding that science has spent a century trying to understand. From the stillness before, to the first breath of expansion, to the faint hum that still echoes through the night sky, every trace we observe whispers part of that story. The Big Bang Theory is not just an idea. It is the quiet framework that holds together the history of everything we know, a theory that began with mathematics, with observation, and with an awareness that even the void between galaxies is not empty but expanding. Take a slow breath. Imagine the universe not as a fireball in darkness, but as space itself, stretching soft, continuous, without edges. Every point in the universe moves away from every other, not because of a blast, but because the distance between them grows. Expansion itself is the motion. Creation through geometry, not explosion. The foundation of this understanding begins with Albert Einstein and his theory of general relativity, written in 1915. He described gravity not as an invisible force pulling between masses, but as the bending of space and time by energy. A planet curves space. A star curves time. Even light, though weightless, follows the shape of that curvature. Einstein's equations were elegant, balanced, but they implied something strange. If the universe had mass, then its fabric could not stand still. It must either stretch outward or fold inward. Change was built into its structure. Yet Einstein himself hesitated. He added a cosmological constant, a kind of counterforce to make the universe remain static, thinking that eternal stillness must be the natural order. He didn't yet imagine that the cosmos could be alive with motion. But just 7 years later, a Russian mathematician named Alexander Friedmann dared to solve Einstein's equations differently. In 1922, Friedmann showed that an expanding universe was not just possible, it was a natural consequence of the math itself. Space could grow. Distances could stretch. Galaxies could drift apart like dust carried by an unseen tide. Then came Georges Lemaitre, a Belgian priest and physicist who in 1927 proposed something quietly radical, that the universe had a beginning. He called it the primeval atom, a single dense point that contained all that would ever be. When it expanded, it did not do so into space. It created space. It created time. It was not an explosion in a void, but the birth of the void itself. At first, few listened. The idea of a cosmic beginning felt uncomfortably close to creation myths. Many scientists preferred an eternal universe, constant and unchanging, infinite in both directions of time. But the cosmos was already speaking, and soon its evidence began to reach us through light. In the 1920s, Edwin Hubble studied distant galaxies through the Hooker telescope on Mount Wilson. He noticed that nearly all of them showed a shift in their light toward the red, a red shift. It was as if their light waves were stretched, lengthened by distance. Hubble compared that red shift with how far away the galaxies appeared to be. And from that relationship came a simple but profound law. The farther away a galaxy is, the faster it is receding from us. This became Hubble's law, the first observational proof that the universe is expanding. It meant that space itself was stretching in all directions, carrying galaxies with it. Not flying through space, but carried by space. If everything is moving apart now, it follows that in the past, everything was closer together. Go back far enough and you reach a time when everything, all matter, all energy, all the fabric of reality was compressed into an infinitesimal point. That moment extrapolated from the expansion is what we call the Big Bang. The universe in this view is not a fireball spreading through emptiness, but a warm ocean cooling as it expands. A cosmic breath, long, slow, continuous. Even now, billions of years later, it continues to expand. The distance between stars increases. The wavelengths of ancient light stretch, and the universe grows quieter, more diffuse, but never still. Then, in 1964, two engineers, Arno Penzias and Robert Wilson, were testing a radio antenna in New Jersey. They found a faint background hiss that would not go away. It came from every direction, day and night, no matter where they pointed the receiver. At first, they thought it was interference, maybe pigeons nesting in the dish. But after careful cleaning, the hum remained. It was not local. It was cosmic. That hum turned out to be the cosmic microwave background, the ancient radiation left over from the early universe, the residual glow of the Big Bang itself. Predicted years earlier by George Gamow, Ralph Alpher, and Robert Herman, This faint afterglow confirmed what Lemaitre and Friedman had described. The universe had indeed begun hot, dense, and luminous, and had cooled as it expanded. Today, that radiation fills all of space at a temperature of 2.725 Kelvin, just above absolute zero. It is nearly uniform, smooth across the sky, with only the tiniest variations, 1 part in 100,000. Those small fluctuations are the fingerprints of the first ripples in the cosmic fabric, the seeds from which galaxies and clusters would later grow. From Einstein to Hubble to the cosmic afterglow, the picture became clear. The Big Bang was not speculation, but structure. A theory confirmed by multiple independent pillars of evidence. We can summarize them as 4 quiet truths. Cosmic expansion, galaxies moving away, space itself stretching, cosmic microwave background, the faint relic heat of the young universe, primordial light elements, the abundance of hydrogen, helium, and lithium matching predictions from nuclear physics, cosmic evolution, the observation of galaxies and stars forming over time, consistent with models of a universe aging and cooling. These observations together form the cornerstone of modern cosmology. Not a belief, but a network of consistent, testable realities. Each one strengthens the others. Each one is a window into an earlier era. And yet every answer reveals another layer of mystery. If the universe has been expanding for 13.8 billion years, what lies beyond that expansion? If time began with the Big Bang, what does it mean to ask what came before time? To imagine the expansion picture the night sky as a great silent canvas. Every star, every galaxy, every beam of light is painted upon it. Now, slowly, the canvas itself stretches. Every brushstroke moves apart from the others, but the pattern remains. The galaxies are not flying through pre-existing emptiness. They are carried on the fabric of space-time itself. This expansion happens everywhere, even now, though too slowly to see within a lifetime. Between galaxies, space lengthens. Within galaxies, gravity holds things together. Your hands, the planet, the sun. They remain bound, small islands in the rising tide of the cosmos. Einstein's equations describe this precisely. Energy and matter tell space-time how to curve. Curvature tells matter how to move. It is a cosmic dance that began the instant expansion began. What began as abstract mathematics has become an observational truth. Astronomers now measure the rate of expansion, the Hubble constant, with increasing precision. They observe galaxies at billions of light years away, their light stretched and softened by the same expansion. They map the cosmic microwave background, tracing the minute temperature differences that formed the scaffolding of structure. And in those measurements, the universe remembers its origin. Every photon of starlight carries history. Every particle of dust drifts in the echo of that first fire. Even the atoms in your body, hydrogen, carbon, oxygen, are distant descendants of that same beginning. When you gaze into the night sky, you are not seeing distance alone. You are seeing time. Because light has a finite speed, to look far is to look back. The nearest star appears as it was 4 years ago. The nearest galaxy 2.5 million years ago. The light from the most distant galaxies, the ones we capture in deep field images, began its journey when the universe was still young. The cosmic microwave background itself is light from 380,000 years after the Big Bang. a baby picture of the cosmos, faint but intact. It shows us the moment the universe first became transparent, when light could travel freely through space. Before that, the cosmos was a sea of plasma, glowing but opaque. After that, it began to cool, to gather, to form. And so, when we observe, we are not just seeing outward but backward into epochs of unimaginable density and temperature, into the first pages of cosmic time. Even with all this motion, galaxies drifting apart, light stretching, space swelling, there is a strange stillness that underlies it all. From any point in the universe, the view looks much the same. There is no center, no edge, no preferred direction. This uniformity is called the cosmological principle, and it holds that the universe is homogeneous and isotropic on large scales. Everywhere, it is expanding equally. It's a paradox that brings calm motion without chaos, expansion without direction, like a tide that rises evenly across every shore. From within, there is no boundary to cross, no center to leave behind. Only distance growing and time unfolding with it. The Big Bang Theory does not claim to describe the origin of existence itself. Rather, it describes the evolution of the universe from that first observable moment onward. It tells us how energy became matter, how simplicity grew into structure, how radiation cooled into atoms and atoms into stars. It explains not the cause, but the consequence, the path from heat to light to life. To ask what caused it is to ask what came before time. And that question leads us into regions where physics begins to tremble, where our equations no longer hold. We call that region the Planck epoch, the first 10, 43, 10, 10, 43, 10, 43 seconds a moment, so brief and so dense that even the laws of general relativity cannot describe it. In that silence, all known forces may have been one, and from that unity, the diversity of the cosmos unfolded. But before we reach that point, before the forces separate and the first particles form, we must look deeper into how light carries time itself, how every photon becomes a messenger from the early universe, and how by studying that ancient light, we glimpse the memory of creation. The Big Bang is not an answer, it is an opening, a question written in the sky in every wavelength of radiation, a question that begins quietly. If all of this began from one moment, what began that? Let that thought drift like starlight across your mind, soft, patient, infinite in its return. The universe as we know it is not just a space we inhabit, it is a memory we live inside. Every particle of light that reaches your eyes tonight began its journey long ago. It traveled through the slow breath of expanding space, crossed the depths between galaxies, and arrived here a silent witness to time. Light is our messenger from the past. It tells the story of where we came from, not in words, but in wavelengths. And by learning how to listen to its faint and endless voice, we begin to understand the universe not as a single instant, but as a continuous unfolding. A history written in photons, stretched by expansion, softened by distance, yet still shimmering with truth. Let your thoughts drift gently now from the idea of the universe's birth to the light that still carries its memory. Because when we study light, we are not merely looking outward, we are looking backward, deep into the origin of time itself. Every beam of starlight, every flicker from a galaxy, is a thread connecting this present moment to something far away and long ago. In human experience, light feels instant. You turn on a lamp and the room glows. The delay is too small to feel. But on the cosmic scale, light is slow enough to reveal the structure of time. It moves at a constant speed of about 300,000 kilometers per second, fast enough to circle the Earth 7 times in 1 second, yet not infinite. And that finiteness makes it precious. It gives us a way to measure time across distance. A single unit of that distance is called a light year. The space light travels in 1 year about 9.46 trillion kilometers. To speak in light years is to weave time and space together as nature does. Light from the moon takes a little over 1 second to reach us. Light from the sun, our nearest star, takes 8 minutes and 20 seconds. When you look at the sun, you are seeing it as it was 8 minutes ago. And when you gaze at Andromeda, our neighboring galaxy, the faint shimmer you see tonight began its journey 2.5 million years ago, when early humans were just beginning to shape tools from stone. The night sky in this way is not a map of what is, but of what was. Each star belongs to a different era. Each glimmer is a timestamp, an ancient echo woven into the present. Even the Milky Way, stretching across the darkness, is not a single instant, but a collage of millions of moments layered together in light. Einstein's relativity teaches that space and time are not separate things. They are threads in the same fabric, a continuum that bends under mass and energy. We call it space-time, and light moves along it at the fastest speed possible. But because light's speed is fixed, it turns distance into a kind of memory. The farther away something is, the older its light becomes. To look into the cosmos is to look into history. Telescopes, then, are not merely instruments of sight. They are time machines catching light that began its journey before Earth even existed. When astronomers study galaxies billions of light years away, they are seeing the universe as it was billions of years ago. Each photon is an arrival, a traveler that has crossed the ages. It tells us what the universe once looked like, smaller, denser, younger. In this way, the sky is not just vast, it is layered. Each distance holds a different epoch. The nearby stars are recent in cosmic time. The farthest light we can see, the cosmic microwave background, is the earliest visible trace of existence itself. The cosmic microwave background, or CMB, is the oldest light we can observe. It is the faint uniform glow that fills the entire sky like a whisper that never fades. It was released about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form. Before that moment, the cosmos was a blinding fog of plasma electrons and protons so hot that light could not travel freely. Every photon was trapped, scattered endlessly among particles. But as expansion continued, temperature dropped, and electrons joined protons to form neutral hydrogen. Space became transparent. Light was free at last to move. That first freedom is the light we see today as the CMB. Over billions of years, as the universe expanded, the light's wavelengths stretched from visible and infrared down to microwave gentle radiation with a temperature of 2.725 Kelvin. Everywhere we look, it hums the same soft note, a near-perfect uniformity punctuated by tiny ripples, 1 part in 100,000. Those ripples are the seeds of structure. They show where matter was slightly denser, where gravity would later pull gas into galaxy stars, and eventually planets. In that subtle map, frozen in the oldest light, lies the origin of everything we see. When satellites like COBE WMAP and Planck measured the CMB in exquisite detail, they gave us more than an image. They gave us a record of the early universe's geometry. From that faint radiation, scientists deduced the age of the universe, 13.8 billion years, and confirmed that space is astonishingly flat on large scales. That flatness, that calm symmetry speaks of a universe finely balanced, neither curving inward toward collapse nor outward toward chaos. A quiet, stable expansion that has continued for all the ages since. We are not limited to visible light. The universe speaks in many frequencies, each revealing a different layer of time. In radio waves, we see the cold structures of galaxies and the vast filaments of hydrogen between them. In infrared, we glimpse the warmth of dust clouds where stars are born. In ultraviolet and X-rays, we see the violent brilliance of supernova and the radiation around black holes. And in gamma rays, we see the flashes of the universe's most extreme events, the collapse of massive stars, the collision of neutron stars, the brief fierce life of the high-energy cosmos. Together, these wavelengths form the electromagnetic spectrum, a continuous rainbow from long, gentle waves to short, powerful bursts. Each carries information about the conditions in which it was born: temperature, motion, composition. By combining them, we build not just a picture, but a timeline. We can trace the evolution of the universe through its light from the first transparency of the CMB to the slow red glow of distant galaxies. Light in this sense is the universe's autobiography, a story told not in words, but in color, frequency, and rhythm. And every photon that reaches us adds another page to that endless cosmic diary. Imagine the farthest galaxy we can observe, one whose light has traveled for nearly 13.5 billion years. What we see is not what it is now, but what it once was, a small, forming structure in a young universe. The space between us and it has expanded dramatically since that light began its journey. The galaxy itself has changed, perhaps merged with others, perhaps gone silent. But its light remains crossing the void, redshifted and softened like an echo that never quite fades. Every photon stretches as it travels its wavelength, lengthened by the expansion of the universe itself. What was once bright ultraviolet becomes faint infrared. What was once heat becomes cold radiation. This stretching, this redshift, is one of the most beautiful signatures of cosmic time. It tells us how far the universe has expanded since the light began its journey. It turns motion into color, distance into song. As we move through the next chapters, we will speak more of this redshift, of how it confirms expansion, how it reveals the rate of cosmic growth, how it measures time, not by clocks, but by light itself. But for now, simply rest with this thought. When you look at the night sky, you are surrounded not by stars in the present, but by memories. Beams of light that have traveled across ages, unchanged yet always aging. They show you the past, and in doing so, they show you your place within time's flow. It's humbling to realize that our ability to see at all, to know, to understand, depends on light's patience. If it traveled infinitely fast, we would see everything as it is now, but we would never glimpse its history. There would be no sense of before, no measure of change, no story. Because light takes time, we can trace evolution. We can see galaxies forming stars, aging clusters, merging. We can watch the universe grow from youth to maturity. The delay is not a flaw. It is the gift that lets us see the past unfold. Even our sun shining steady in the sky is already old news. Every photon of sunlight that warms your skin left the sun when you were still a few minutes younger. Every ray from a distant star began its journey before you were born. And every pulse of ancient light that fills the background sky began before Earth had oceans, continents, or life. The universe, in a way, is a mirror made of time. Everything you see is both real and remembered. And in that layering, that endless reflection of light through distance, the cosmos becomes both vast and intimate. As light travels farther, it grows dimmer, stretched until it slips beyond the reach of our instruments. There comes a distance so great that its light will never reach us, not because of obscurity, but because of expansion. Beyond a certain horizon, the space between galaxies expands faster than light can cross. Those regions recede from us forever, not hidden by obstacles, but by the fabric of space-time itself. This horizon defines the observable universe, a sphere roughly 93 billion light-years across. Everything inside it is part of our cosmic view. Everything beyond it remains forever unseen, not because it does not exist, but because its light has not and will not have time to arrive. We live then in a visible bubble surrounded by ancient light. Beyond that bubble there may be endless continuation, more galaxies, more structures, more unknown. But from here, we see only what time allows. We see the memory of the universe, not its entirety. And yet this partial vision is enough to trace its history, to reconstruct its evolution, to feel its immensity. Through light, we are connected to the whole. Time itself is shaped by the same geometry that guides light. When gravity bends space, it bends time as well. Near massive objects, clocks tick more slowly. Light curves as it passes, stars its path arched by the invisible well of gravity. We observe this bending gravitational lensing in the sky where distant galaxies appear stretched into arcs and halos around closer clusters. These distortions are not errors, but maps the universe revealing its own architecture through light. Every curved ray, every faint echo, every delay in time becomes a clue to how space-time itself is shaped. Light, time, and space are not separate things. They are facets of the same endless surface rippling together in quiet harmony. And in that harmony, we find the story of everything, a universe expanding, cooling, evolving. A cosmos whose light has never stopped traveling, never stopped carrying the past into the present. So when we speak of the Big Bang, we are not speaking only of a beginning. We are speaking of light that has never stopped arriving, of time that has never stopped unfolding. Every observation, every telescope, every photon is part of that same moment, extended a continuous dawn that still glows in microwaves, in starlight, in your own reflection beneath the night sky. In every sense that matters, the Big Bang never ended. Its light still fills the universe. Its time still expands through us. And as we look outward, we look back into that radiant memory into the stillness before everything began. Let the thought settle as if light itself were a breath moving through you. Quietly, steadily, endlessly. Light stretches as it travels, not because it grows tired, but because the universe itself is breathing. Every moment, space extends quietly, invisibly, pulling the waves of ancient light wider, softer, redder. From this gentle stretching, we have learned one of the universe's most profound truths. Everything is moving apart, not drifting through emptiness, but carried by the growth of space itself. Let your thoughts return for a moment to the images from the last part. Galaxies far away. Light arriving late, the cosmos unfolding like a memory. Each of those lights carries a subtle message, a shift in its color, that reveals how far it has traveled and how much the universe has changed along the way. This is what astronomers call redshift, the quiet language of expansion. To the eye, redshift is invisible. The colors of stars and galaxies appear fixed, like still points in the dark. But through a spectroscope, an instrument that spreads light into its component wavelengths, those colors reveal delicate patterns like musical notes. Every element in the universe leaves its own fingerprint in light, hydrogen, helium, oxygen, iron. Each emits or absorbs specific wavelengths, narrow lines across the rainbow of starlight. When astronomers compare those lines from distant galaxies with the same lines measured in laboratories on Earth, they find something extraordinary. The patterns are shifted toward the red end of the spectrum. The farther the galaxy, the greater the shift. This means that the light waves have been stretched during their journey. And the only thing capable of stretching light on such scales is the fabric of space itself. This is the cosmic Doppler effect, but unlike the sound of a siren moving away, which fades in pitch, because the source is changing position in air, the cosmic redshift occurs because the air itself, the medium of space-time, is expanding. Space grows and light grows with it. Each wave that leaves a star begins at a certain frequency, but as it crosses the vastness between galaxies, space swells and the distance between peaks widens. The color softens, the light reddens, the message of expansion is carried in its hue. Every redshifted photon is a syllable in the universe's unfolding story. From nearby galaxies, the shift is small, a quiet murmur in the data. From faraway quasars, it is enormous. The light stretched so far that what began as ultraviolet ends as deep infrared invisible to human eyes. Astronomers measure this change with a number called Z, the redshift parameter. When Z is small, a galaxy is near. When Z grows large, we are looking into ancient epochs where the universe was younger and denser. At Z equal 1, light has been stretched by a factor of 2. At Z equal 7 or 8, we are seeing the first galaxies, fragile glimmers formed less than 1 billion years after the Big Bang. And beyond that, at Z equal 1100, we reach the light of the cosmic microwave background, the oldest light of all. Through redshift, distance becomes history, color becomes time, and the night sky becomes a record of motion, galaxies, receding light, expanding creation, continuing. The story of redshift truly began with Edwin Hubble in the 1920s, when he measured the distances to nearby galaxies using a class of variable stars known as Cepheids. These stars pulse with regular rhythms, and their intrinsic brightness can be inferred from the rate of that pulse. By comparing their true brightness to their observed brightness, Hubble estimated how far away they were. When he compared those distances to the redshifts of their spectra, a pattern emerged. The greater the distance, the greater the redshift. Galaxies farther away were receding faster. This linear relationship velocity, proportional to distance, became Hubble's law, and its constant of proportionality, HO, became one of cosmology's most important numbers. It told us that the universe was not static as once believed, but expanding. Everywhere in every direction, galaxies are moving apart, not because they are flying through space, but because space itself is stretching between them. It was as if the universe were a great fabric, and every galaxy was a bead sewn into it. When the fabric stretches, the beads move apart, though they never move across the cloth. The space between them simply grows. From Earth, the expansion feels abstract. The night appears still. Stars hold their places. Galaxies drift too slowly for us to notice with our eyes. But on scales of billions of light years, expansion shapes everything. If we could watch the universe in time-lapse, the galaxies would appear to drift apart like islands on a widening sea. Clusters would stay bound, held together by gravity, but the space between clusters would expand relentlessly. Light from distant objects would stretch, fade, redden its energy, diluted by the growth of space. The same light that once shone bright and blue now hums in radio waves cooled by eons of expansion. The universe itself is aging through its light. Hubble's discovery changed not only astronomy, but philosophy. For the first time, humans understood that the cosmos had a history, that it was not eternal and unchanging, but dynamic, evolving with a past and perhaps a future. The redshift was not just evidence of motion, it was evidence of time. Modern astronomers have refined Hubble's work with astonishing precision. They use Type Ia supernova exploding stars of known brightness as standard candles, measuring how their light fades with distance. They calibrate distances using Cepheid variables and cross-check with the cosmic microwave background itself. Each method gives a value for the Hubble constant, though they don't all agree exactly. Some measurements suggest around 67 kilometers per second per megaparsec, others around 73. This difference, known as the Hubble tension, may be a clue that new physics waits beyond our current models. Still, the overall picture remains clear. For every million parsecs of distance, about 3.26 million light-years, the universe's expansion adds roughly 70 kilometers per second of recession velocity. That number, multiplied by the vast distances between galaxies, produces cosmic speeds almost beyond imagination. And yet all of this motion is relative not through space, but of space itself. Galaxies are not rushing outward into pre-existing emptiness. The emptiness is being made, because the expansion rate sets the rhythm of cosmic history. It also gives us a way to estimate how long the universe has been expanding. By working backward from today's Hubble constant and the observed deceleration and acceleration of cosmic expansion, scientists infer an age of about 13.8 billion years. This is not the age of any particular star or galaxy, but the age of space-time itself, the time since the scale of the universe was effectively zero. When you look at a galaxy 10 billion light-years away, you see it not as it is, but as it was when the universe was only a few billion years old. The redshift tells you how much the cosmos has expanded since that light began. It is both a measure of time and of growth. And so through redshift, we see not only how far light has traveled, but how much the universe has aged along the way. The greater the redshift, the deeper we look into the universe's childhood. The smaller the redshift, the closer we are to the present moment. Between them stretches the long, luminous timeline of existence. When we think of expansion, it is tempting to imagine sound and explosion, a roar, a wave of creation sweeping outward. But the universe expands in silence. There is no air, no medium for sound to travel through. Only the vibration of light, the hum of gravity, the rhythm of time. Even now, galaxies move apart in silence. The redshift of their light is the only audible note in this cosmic symphony, a frequency lowered by distance, a tone drawn out by the stretching of space. Each photon leaves its source with a particular wavelength, and as it travels, that wavelength elongates. It is as though time itself inhales, and every breath widens the distance between peaks of the cosmic wave. What we see as red is simply the slowing of light's ancient song, not decay but transformation. A record of movement woven into the color of the cosmos. At the farthest edges of observation, the redshift grows immense. Light from the earliest galaxies is stretched by factors of 10 or more. Its energy diminishes. Its color fades beyond visible range into the cool whispers of infrared and microwave. Eventually, at extreme distances, redshift does something extraordinary. It hides things forever. There exists a boundary called the cosmic horizon, beyond which light can no longer reach us, not because it is too faint, but because the expansion of space carries those regions away faster than light can cross. That horizon defines the limit of our view, the edge of the observable universe. Everything beyond it is still part of the cosmos, but it will never be seen from here. The redshift there is infinite. Light never arrives. This is not an edge in space, but in time, a horizon of possibility always receding, always unreachable. As light stretches, it loses energy. Each photon's wavelength grows longer, its frequency lower, its power diminished. But the energy does not disappear. It becomes part of the universe's gentle cooling. The radiation that once filled the cosmos with blinding heat has softened into the faint glow of the microwave background. The same process continues now, cooling starlight, dimming galaxies, slowing the heartbeat of creation. This energy loss is not destruction, it is transformation. The universe trades brilliance for breadth, heat for harmony. The expansion is the universe's way of redistributing energy, spreading it thin across the vastness of space-time. It is how eternity cools. The concept of redshift might feel distant, abstract, far removed from daily life, but in a quiet way it mirrors the passage of time itself. As moments stretch, memory softens. What was once vivid fades into gentle tone, like light sliding down the spectrum. The redshift of light and the aging of experience are two faces of the same truth, that everything given enough distance drifts toward calm. Even here on Earth, redshift can be measured in small ways. Light climbing out of a gravitational field, say from the surface of a massive star, loses a little energy just as cosmic light loses it to expansion. It reddens ever so slightly. A universal law to climb out of gravity or to travel through growing space is to stretch. And perhaps that is a kind of poetry, the universe in all its forms, lengthening its light to reach us. From the earliest moments after the Big Bang expansion has defined everything, it set the rhythm of time, the shape of space, the balance between energy and matter. Redshift is the echo of that rhythm, a record of motion written across the sky. Galaxies bound within clusters drift apart from other clusters. Superclusters form filaments and walls around great cosmic voids, regions of emptiness that expand faster than the structures that surround them. This web of matter, the cosmic web, is the large-scale structure of the universe sculpted by gravity but stretched by expansion. The redshift of distant light allows astronomers to map this web to trace its threads through billions of light years to see how galaxies are arranged like beads on invisible strings. Even now, as we observe, the web grows slowly, silently, like frost forming on glass. Every observation, every measurement, every spectrum confirms what began as a mathematical dream, that the universe expands and has always expanded since its first moment. And with each passing second, that expansion continues. The wavelengths of light grow longer. The distances between galaxies widen. The temperature of the cosmic background cools. It is a motion so vast and steady that we do not feel it. We live inside it. We are part of it. The redshift is not just a property of light. It is the pulse of the cosmos itself, the mark of creation still unfolding. It is proof that the Big Bang never truly ended. It continues in every moment, in every stretching wave, in every fading star. When you look into the night sky, remember, the redness of distant galaxies is the universe's heartbeat. Each shift in color is time expanding space, growing history, deepening. Each photon carries the signature of motion that began before there were galaxies, before there were stars, before there was even form. And in that realization lies something serene, a sense that everything moves together, yet nothing is lost. The universe stretches, and in doing so, it preserves. Every moment, every atom, every breath exists within this same rhythm of expansion. The redshift is how the cosmos speaks softly and continuously across the silence of space. From the soft red light of galaxies, we drift further back beyond the stars, beyond the first clusters of matter into a time when light itself was still trapped. It is here in the silence before transparency that we find one of the universe's most delicate relics, the cosmic microwave background, the faint, cold whisper of creation that fills all of space. It hums quietly everywhere, night and day, across every direction of the sky. You cannot see it with your eyes, yet it surrounds you. You can feel it faintly in the static of a television screen, in the hiss between radio stations, a memory older than stars, older than galaxies, older than everything that breathes. If the redshift of galaxies is the rhythm of expansion, then the CMB is its lingering echo, the still glowing afterimage of the Big Bang itself. Before this light could travel, the universe was dense beyond imagination. A fog of protons, electrons, and photons locked together in a constant exchange of energy. Every particle of light was scattered again and again by matter unable to travel more than a tiny fraction of a millimeter before colliding. The universe was not dark, but blinding, a seething, opaque plasma uniform in brightness, yet restless. As space expanded, the temperature dropped. At around 3,000 Kelvin, roughly 380,000 years after the Big Bang, the particles of matter cooled enough for electrons and protons to join, forming the first neutral atoms. This moment is known as recombination, though nothing was being recombined since atoms were new. With electrons bound into atoms, the fog cleared. Light was free. Those photons once trapped in the early universe's radiance began their journey outward, spreading in every direction, filling space evenly. They have been traveling ever since. In every cubic meter of the universe, billions of them drift remnants of that first transparency. Over time, as the universe expanded, their wavelengths stretched from brilliant visible light to the gentle microwave range. Their temperature fell from thousands of degrees to just 2.725 Kelvin, only a whisper above absolute zero. What was once fire became frost. What was once a glare became a glow. For most of human history, the cosmos was thought to be cold and silent between the stars. But in 1948, George Gamow, Ralph Alpher, and Robert Herman predicted that if the Big Bang were real, its residual heat would still fill the universe, not hot, but cooled to a few degrees above absolute zero. They calculated that we might detect this ancient radiation if only our instruments were sensitive enough. Their prediction went largely unnoticed, folded quietly into theoretical papers. Then, in 1964, two engineers, Arno Penzias and Robert Wilson, working at Bell Laboratories in New Jersey, were testing a large horn antenna meant for satellite communication. They were troubled by a persistent noise, a soft hiss that would not go away. They cleaned the equipment, removed nesting pigeons from the dish, recalibrated every circuit. Yet the hum remained constant isotropic, coming from all directions equally. At the same time, a few miles away, a group at Princeton University, led by Robert Dickey, was preparing to search for the very signal Gamow had predicted. When Penzias and Wilson shared their findings, the connection became clear. They had stumbled upon the afterglow of creation. That faint noise was the cosmic microwave background, the oldest light in existence. The discovery confirmed the Big Bang model more powerfully than any telescope image ever could. It was not a theory, now it was an observation, a presence, a cosmic memory woven into every corner of space. For their work, Penzias and Wilson received the Nobel Prize in Physics in 1978. But even they understood the humility of what they had found. The universe itself had whispered to them, and they had simply listened. To human eyes, the CMB is invisible, its wavelength too long for our vision. But to radio telescopes, it paints a complete image of the cosmos as it was nearly 14 billion years ago. At first glance, it appears astonishingly uniform. The same temperature, the same faint intensity, no matter which direction one looks. This uniformity tells us that the early universe was incredibly smooth, the same in every direction. Yet, with more sensitive instruments, subtle variations emerge. Tiny differences in temperature, just 1 part in 100,000, appear as mottled patches across the cosmic sky. These small ripples are everything. They are the seeds from which all structure in the universe grew. Regions slightly denser in matter pulled in more gravity-gathering gas-forming stars than galaxies. Regions slightly thinner remained empty, becoming the vast cosmic voids we see today. From these minute imperfections, the universe's faint unevenness, came the entire architecture of the cosmos. 3 missions have traced this faint pattern in exquisite detail. The COBE satellite, launched in 1989, first confirmed that the CMB follows the precise blackbody spectrum predicted by theory, a near-perfect curve matching a temperature of 2.725 Kelvin. Its measurements proved that this radiation is truly cosmic, not from stars or galaxies, but from the birth of space itself. For this, John Mather and George Smoot received the 2006 Nobel Prize in Physics. Then came WMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001. It mapped the entire sky with far greater precision, revealing the exact scale of those early ripples. From WMAP, cosmologists deduced the universe's composition about 4.9% ordinary matter, 26.8% dark matter, and 68.3% dark energy. A cosmos mostly unseen but not unknowable. Finally, the Planck satellite, launched in 2009 by the European Space Agency, provided the most detailed map of the CMB to date. Its resolution was so fine that each pixel represented only a few arc-minutes of the sky. From its data, scientists refined the universe's age, 13.799 plus 0.021 billion years, and confirmed that space is astonishingly flat, curving less than 0.4% from perfect Euclidean geometry. The patterns of temperature and polarization in the CMB also revealed the earliest whispers of quantum fluctuations stretched to cosmic size by inflation, the brief explosive growth that occurred a fraction of a second after the Big Bang. The CMB is more than radiation. It is geometry made visible. It encodes the size, shape, and curvature of space itself. By measuring the angular scale of those tiny temperature fluctuations, scientists can determine whether the universe is open-closed or flat. If the universe were positively curved like the surface of a sphere, those hot and cold spots would appear larger. If it were negatively curved like a saddle, they would appear smaller. What Planck revealed was balance. The universe is flat to within a fraction of a percent. This flatness means that the total density of matter and energy in the cosmos precisely matches the critical value needed to halt curvature. It is as if the universe began with a perfect equilibrium, a harmony so fine that even slight deviation would have led to a radically different reality. This balance is one of cosmology's deepest mysteries. Why should the universe begin poised so perfectly between expansion and collapse? The answer may lie in cosmic inflation, which we will explore soon, a theory suggesting that a brief exponential expansion smoothed and flattened everything before the cosmos cooled. For now, the CMB remains the frozen evidence of that perfection, the visible calm after a storm of creation. When scientists translate the fluctuations of the CMB into sound frequencies, something remarkable emerges. The early universe had a tone. Pressure waves rippled through the hot plasma like vibrations in air, producing a faint cosmic hum, the first music of existence. These acoustic oscillations left their imprint on the CMB as alternating bands of density like standing waves in a vast, resonant chamber. By analyzing these patterns, cosmologists can measure not only the universe's composition, but also its expansion rate in the first moments. The rhythm of those primordial vibrations still echoes in the clustering of galaxies today. Each beat, each rise and fall in density corresponds to a harmonica note in the cosmic chord that played before stars were born. To listen to the CMB is to hear the sound of light finding its freedom. A silent melody that has lasted 14 billion years. What is most humbling about the CMB is its universality. It does not belong to any one direction, any one point of view. It is everywhere, constant, impartial. Every observer, wherever they are, sees it the same. From the edge of our solar system to the farthest galaxy, the same background hum fills the void. If an intelligent being in another galaxy were to measure it, they would find the same temperature, the same patterns, the same ripples in intensity. We are all bathed in the same ancient light. This shared illumination makes the CMB not just a scientific relic, but a unifying presence, a reminder that everything that exists now once glowed as one. It is the thread that connects all matter, all galaxies, all life. The night sky is not separate from you. It is your origin, your inheritance. As the universe continues to expand, the CMB cools. Its temperature decreases in perfect proportion to the growth of space. When the universe was half its current size, the background was twice as warm. When it was a tenth its size, the background glowed 10 times hotter. This steady cooling is a clock, a measure of cosmic time written in temperature. Eventually, billions of years from now, the CMB will cool further, fading into wavelengths so long that no instrument can detect them. The universe will grow darker, quieter, more transparent still. But the photons themselves will remain redshifted beyond measure, stretched into the rhythm of eternity. The CMB reminds us that even the faintest light endures. Across unthinkable distances, across eons of cooling and expansion, it persists, softened but not gone. It is the universe's oldest memory, and it glows still even now around you. Together with the expansion of galaxies and the abundance of light elements, the CMB forms one of the 3 great pillars of Big Bang cosmology. It is direct evidence that the universe once existed in a hot, dense state, and that it has cooled over time. No other model, no static universe, no eternal steady state can account for this radiation's spectrum or uniformity. The CMB is the proof that the universe remembers. It remembers being small. It remembers being bright. It remembers becoming transparent and setting its light free. When you imagine the cosmic microwave background, you are seeing the first dawn, the moment when the universe's blinding fog gave way to clarity. It is a picture of everything before stars began to shine, before the first galaxies gathered, before time had rhythm beyond expansion. This light has crossed every age unchanged except for its cooling. It has watched the birth of galaxies, the ignition of suns, the rise of worlds, the emergence of consciousness, capable of wondering about its own beginnings. You are part of that same light. Every atom in your body once swam in that glowing plasma. The photons that touch your skin tonight have shared their journey with your atoms for billions of years. In every sense, you are made of the universe's first breath. The cosmic microwave background shows us what the universe looked like when it was 380,000 years old. But what about before that? What happened in the first seconds when matter was still forming, when light was still caged in the dense fire? What did the universe look like in the moments too early for even photons to escape? To answer those questions, we move deeper into the first minutes when atomic nuclei formed, and into the first fractions of a second when the laws of physics themselves began to take shape. The CMB is our doorway, the threshold between what we can see and what we must imagine. Let your mind rest there for a moment on that border between light and darkness. Feel the calm of an ancient glow that still surrounds you. The universe continues to expand, cool, and whisper softly through time. The light of the cosmic microwave background carries us to a universe already cooling, already transparent. But before that gentle glow, before atoms and photons drifted freely, there was a more urgent, fiery time. A moment when the universe itself was a furnace dense and blinding, filled with energy, intense enough to forge the very first elements. This is the era known as Big Bang nucleosynthesis, or BBN, the time when the first atomic nuclei formed when the universe learned the art of structure. It was brief, only the first 20 minutes of cosmic time, yet within that small window, the fundamental chemistry of existence was written. Let your thoughts drift back beyond the calm of the CMB into this earlier heat. Not chaos, but creation quiet in its inevitability, precise in its unfolding. The furnace from which all later stars would inherit their fuel. When the universe was less than a second old, it was pure plasma, a sea of quarks, gluons, photons, neutrinos, and energy, so immense that matter and radiation were indistinguishable. Temperatures hovered around 10 billion Kelvin densities, far beyond the heart of any star. Every particle collided, scattered, annihilated, and formed again in a seamless exchange between energy and matter. In that first second, forces began to take shape. Gravity separated from the unified field. The strong nuclear force began binding quarks into protons and neutrons, and the weak force began guiding their transformations. The universe was expanding rapidly, cooling with every moment, yet still dense enough for the fundamental interactions to sculpt its destiny. As the temperature dropped below about 10 billion Kelvin, protons and neutrons could exist stably. Their dance was governed by the weak interaction, a process that allowed one to transform into the other through the emission of neutrinos. For every 6 protons, roughly 1 neutron remained a delicate balance that would determine everything to come. Already the blueprint for future stars and galaxies was forming, not in structure, but in composition. By the time the universe reached 1 second old, expansion had slowed enough for a kind of rhythm to settle. The temperature fell to around 10 billion Kelvin and neutrinos. Those ghostly, nearly massless particles decoupled, slipping free from matter and streaming outward forever. They became the first messengers, the first relics of a time even older than light. As seconds passed, the universe cooled to about 1 billion Kelvin. In this window, protons and neutrons collided and began to fuse. Hydrogen combined with neutrons to form deuterium-heavy hydrogen. 2 deuterium nuclei joined to make helium-4 the most stable light element. A few rare reactions produced helium-3 tritium and small traces of lithium and beryllium. This process, Big Bang nucleosynthesis, lasted only a few minutes, from roughly 1 second to 20 minutes after the beginning. After that, the universe expanded too much, cooled too far, and fusion ceased. The fire went out. The result was simple, elegant, and universal: about 75% hydrogen, 25% helium, and trace amounts of the others, a ratio that still defines the cosmos today. Every star, every cloud, Every breath of gas between galaxies carries that signature. These primordial elements were the foundation for everything to come. From hydrogen, stars would ignite. From helium, fusion would later produce carbon, oxygen, and the heavier elements of life. But in those first minutes, the universe's chemistry was childlike in its simplicity. No carbon yet, no nitrogen, no iron, just the first most basic ingredients. The cosmos was a sea of light nuclei, drifting in a bath of radiation, awaiting the next act of creation. In the language of numbers, the ratio of protons to neutrons set the cosmic recipe: about 7 protons for every neutron. From this, nearly 1/4 of all matter became helium. It was not random. It was precise, the direct outcome of physics unfolding according to its laws. If there had been just slightly more matter, or slightly less expansion, fusion would have gone further, consuming all hydrogen into helium, leaving no fuel for future stars. If the universe had expanded faster, hardly any helium would have formed at all. But balance prevailed. Enough hydrogen survived for stars to form. Enough helium existed to shape the chemistry of everything that followed. It was a moment of exquisite tuning, a harmony between heat and time, density and decay. Even in its earliest fire, the universe was gentle with its own creation. Today, astronomers test the predictions of Big Bang nucleosynthesis by measuring the abundances of these light elements in the oldest regions of the universe, ancient gas clouds, metal-poor stars, and distant galaxies. Every observation matches the theory with extraordinary precision. Helium makes up roughly 1/4 of the baryonic mass of the cosmos, exactly as predicted. Deuterium, fragile and easily destroyed in stars, survives only in the coldest untouched clouds, and its abundance aligns perfectly with the calculations of early fusion. Even lithium, though slightly less consistent due to stellar processing, fits within the expected range. This agreement is one of cosmology's triumphs. It tells us that the same physical laws, the same constants of nature, governed both the first moments and the world we live in now. Across billions of years, the universe has remained faithful to its own mathematics. The light elements are fossils of that truth. They are not just matter, they are memory. Every atom of helium in the air, every trace of deuterium in the sea is a remnant of those first 20 minutes of cosmic time. As fusion faded, the universe continued to expand and cool. At about 3 minutes, the temperature had dropped below 1 billion. Kelvin, still hotter than any star's core, yet too cool for new nuclear reactions. At this point, radiation dominated, flooding space with photons that outnumbered particles of matter by 1 billion to 1. The universe entered a long, glowing pause. Matter existed but could not yet gather. Gravity's hand was weak against the pressure of radiation. Only much later, when the universe was hundreds of thousands of years old and had cooled enough for neutral atoms to form, could light travel freely, giving rise to the cosmic microwave background we now observe. And so between BBN and the CMB, there stretched an era of waiting, the dark age before light, when the universe was filled with invisible radiation and drifting hydrogen, slowly cooling, slowly preparing for structure. From the simplicity of its ingredients, the universe would later cook itself into complexity. Hydrogen, the lightest element, would fuel the birth of stars. Helium, more stable, more bound, would serve as their ash, the residue of cosmic fire. And within those stars, new fusion would create carbon, oxygen, nitrogen, iron, the building blocks of planets, oceans, and life. But none of that could happen without the balance established during Big Bang nucleosynthesis. The precise ratios of hydrogen and helium determined how stars would burn, how galaxies would shine, how long the universe would remain bright. It is easy to think of those early minutes as chaos, but they were in fact remarkably ordered. Physics unfolded smoothly, predictably, with elegance that still resonates through the cosmos. The early universe was not random, it was rhythmic. Each reaction followed the last like notes in a quiet symphony of heat. BBN also gave cosmologists a way to measure time itself. By comparing the predicted abundances of light elements to their observed values, scientists can infer the density of baryonic matter, the amount of normal matter that makes up stars, planets, and us. From that density, they can determine the rate of expansion at the time of nucleosynthesis, linking it to the Hubble constant today. This cross-check between nuclear physics and cosmic expansion is one of the great achievements of modern cosmology. It ties the smallest scale's atomic nuclei to the largest, the entire universe. It shows that the cosmos is coherent from beginning to end, that its laws are continuous across magnitudes of energy and size. The atoms in your body, once part of that fire, obey the same principles now as they did then. Time, it seems, does not erase the rules. It only stretches them gently across eternity. Deuterium, that fragile isotope of hydrogen with one neutron, is particularly telling. It forms easily in the heat of the Big Bang, but is destroyed easily inside stars. Every time a star ignites, deuterium disappears. So the amount of deuterium we find in pristine regions of the universe acts as a fossil record, frozen before any stars existed. In this way, the cosmos keeps its own archives. By studying light from distant unpolluted gas clouds, astronomers can read those archives and confirm that the proportions of hydrogen and deuterium still match the ancient ratio, a quiet testament to the truth of Big Bang nucleosynthesis. The universe remembers even in its smallest atoms. It remembers the temperature of its birth, the density of its youth, the pace of its expansion. It carries that memory in the elements that drift between the stars. After 20 minutes, the universe's temperature fell below 100 million Kelvin. Fusion ceased. The primordial furnace dimmed. What remained was a vast ocean of hydrogen and helium, cooling slowly, expanding endlessly. The first chemical chapter of existence was complete. No new elements would form until hundreds of millions of years later, when gravity gathered gas into the first stars. Those stars would become new forges, reigniting the cosmic flame on smaller, more intricate scales. But for now, the universe rested. Light filled it, but matter slept. It was a time of radiance without structure, potential without form. And yet, within that stillness lay everything to come: galaxies, stars, planets, life, all waiting in the patient chemistry of hydrogen and helium. When you breathe, you draw in hydrogen atoms born in that first 20 minutes of cosmic time. They have never changed, never been destroyed, only cycled through stars, oceans, and air. The water that moves through your body is ancient beyond measure. It's deuterium forged before light could travel freely. The universe is not something that happened long ago. It is happening still through you. The matter that once glowed in the Big Bang's first fire continues its journey, cooled, bound, transformed, but still following the same rhythm. Big Bang nucleosynthesis reminds us that creation does not need endless complexity to begin. It begins with balance, with the quiet dance of heat and time, gravity and expansion. From that equilibrium, everything else can grow. Even now, when you look at the stars, you are looking at the continuation of that same process. Fusion resumed after a long pause. The stars are echoes of that first furnace replaying on smaller scales what the cosmos did once, everywhere at once. As the universe cooled beyond the reach of fusion, matter settled into transparency. Photons freed from constant collision began their endless journey, creating the light of the cosmic microwave background that still surrounds us. But before that great release of radiation, before the fog lifted completely, physics continued to unfold in deeper and stranger ways. What happens when we look back even further to the moment before atoms, before nuclei, before the forces themselves separated? What happened in the universe's first heartbeat, when all the laws of physics were still one? That realm is called the Planck epoch, a place where time itself becomes uncertain, where our equations dissolve, and where the seeds of all forces were planted. To step there is to approach the limits of what we can know, and to stand at the edge of the unknowable. For now, rest in the calm that follows the universe's first fire. Hydrogen drifts. Helium cools. Light hums softly in the distance. The furnace is gone, but its memory remains in every breath, every star, every atom of life. The fire of nucleosynthesis fades behind us now. The universe cools, expands, and rests in its new stillness. Hydrogen drifts softly through darkening space. Helium glows faintly, then falls quiet. But before this calm, before fusion and formation, before even matter as we know it, there was another time. A moment so small that language itself stumbles to describe it. A span of time shorter than a whisper, briefer than a breath. The Planck epoch. This is the first instant of the universe, the first 10 to 4310, 43 per 10, 43 seconds after everything began. Beyond this threshold, the laws of physics as we know them dissolve. Gravity and quantum mechanics, two great frameworks of reality, no longer agree. And in their disagreement lies mystery. To understand the Planck epoch is to stand at the edge of knowledge itself, to look into a realm where equations fail, yet creation proceeds in silence. We call it the Planck time, named for the physicist Max Planck, who discovered that energy comes in discrete quanta packets so small that they define the smallest meaningful measurements of nature. The Planck time, roughly 10 to 43, 10, 10, 43, 10, 43 seconds, marks the smallest interval after which time as we understand it can exist. Below it, the concepts of before and after lose meaning. At that instant, the universe was smaller than a proton. Its temperature reached 13210, 32, 1032 Kelvin, far beyond what any star, any particle accelerator, any physical system could recreate. Space was not yet space as we know it, and time was not yet measurable flow. The cosmos was a quantum foam, a restless sea of energy fluctuations forming and collapsing, rising and vanishing faster than thought. In that storm of uncertainty, all four fundamental forces, gravity, electromagnetism, The strong nuclear force and the weak nuclear force may have been united as one. No separate interactions, no distinct behaviors, just a single superforce folded within a singular geometry. This unity did not last. Expansion began, and with it came separation, a slow unweaving of nature's fabric into the distinct threads we now observe. But for a brief, immeasurable heartbeat, the universe existed as something pure and undivided whole. As the universe expanded and cooled beyond the Planck temperature, the first great division occurred. Gravity, the weakest yet most far-reaching of the four forces, separated from the others. What remained was a single combined interaction known as the grand unified force, which still bound together the strong, weak, and electromagnetic forces. This next phase is called the Grand Unification Epoch, lasting from 10 to 4310, 4310 to 43, to 10 to 36 ton, 36, 10, 36 seconds. During this time, the universe continued to grow, cooling from unthinkable heat to merely extreme. Energy densities dropped, but the fabric of space-time was still turbulent quantum fields rippling through a tiny inflating cosmos. At 10, 36, 10, 10, 36, 10, 36 seconds, another shift occurred. The strong nuclear force, the force that binds quarks together inside protons and neutrons, broke away, leaving the electro-weak force behind. This symmetry breaking released vast amounts of energy, perhaps triggering the sudden and extraordinary expansion we call cosmic inflation. Each of these separations was like a note in the universe's first chord. Unity becoming diversity, simplicity unfolding into structure, a cosmic symphony beginning its first measure. Before the Planck epoch, space itself did not have clear meaning. There was no where because all positions were equivalent. No distance because separation had not yet emerged. But as the first forces differentiated, geometry began to form. The quantum foam stabilized into space-time, a four-dimensional field capable of curvature, expansion, and continuity. In this moment, the metric of the universe, its underlying mathematical description, came into existence. Space acquired the ability to stretch. Time gained the ability to flow. In these properties, the universe found its first structure. We might imagine this transition like the surface of a frozen pond, where a chaotic, roiling liquid suddenly becomes smooth and continuous. From turbulence, order arises. From quantum froth, geometry is born. Yet the memory of that turbulence still echoes. Quantum fluctuations from the Planck epoch were stretched across the cosmos during inflation, becoming the seeds of galaxies billions of years later. Even now, the largest clusters of galaxies trace patterns first etched into space-time by the smallest possible vibrations. The universe remembers everything, even the chaos from which it came. To describe this first moment, our best theories must work together. Einstein's general relativity explains how gravity shapes space-time, how massive objects curve the geometry of the universe. Quantum mechanics explains how particles behave at the smallest scales, how uncertainty and probability define the subatomic world. But when we try to combine them to describe gravity at quantum scales, their equations collapse into infinities. The two frameworks, perfect in their own domains, refuse to coexist in the same instant. The Planck epoch exposes that fracture. We call this the singularity problem, not because a single point exists, but because our understanding, does not. It is not the universe that breaks here. It is our mathematics. Something deeper must lie beneath a unifying description we do not yet possess. Physicists search for it through quantum gravity theory's attempts to weave relativity and quantum mechanics into one fabric. Among these, string theory proposes that the smallest building blocks are not particles, but vibrating strings whose harmonies generate all forces and matter. Another approach, loop quantum gravity, envisions space-time itself as a network of tiny loops, discrete yet connected quantized geometry rather than continuous flow. Both seek the same goal, to see the Planck epoch clearly, to describe the first instant not as a paradox but as a pattern. So far, both remain incomplete. The mystery holds. If we could observe the universe at the Planck scale, it would not appear smooth. It would shimmer with wild motion, its geometry flickering like reflections on disturbed water. Distances, directions, even the continuity of space would fluctuate violently. This chaotic froth is sometimes called quantum foam, the restless foundation of space-time itself. At this scale, energy density is so high that miniature black holes may form and evaporate constantly, their births and deaths creating ripples in the quantum field. The entire cosmos was in essence a single point where probability ruled and certainty did not exist. We cannot yet measure this foam directly. It lies far beyond the reach of any instrument. Yet its consequences may still be visible in the subtle patterns of the cosmic microwave background, in the delicate anisotropies that record the earliest tremors of existence. What seems smooth and still to us today, the vastness between galaxies, began as that flickering uncertain sea. And from its chaos came calm. From its instability order. From its quantum breath time itself began. In human thought, time is flow and endless movement from past to future. But in the Planck epoch, time as flow did not exist. There was no past to move from, no future to move toward. Only quantum potential waiting to unfold. The birth of time was not a sudden ticking of a clock, but the emergence of sequence, the realization that one state could follow another. When energy condensed, when expansion began, when cause could precede effect, the concept of before found meaning. In that instant, causality, the heartbeat of reality, came into being. The universe could now evolve, could change, could remember. From that point forward, time and space were forever entwined. They expanded together, curved together, aged together. And from that bond came everything we know, the slow cooling of light, the rise of galaxies, the deep rhythm of cosmic history. Time began softly, like the first motion in a still sea. As the universe cooled through 1027 Tesher, 1027 Kelvin, the energy of photons could still create matter pairs of particles and antiparticles that appeared and vanished in an eternal dance. For every proton that emerged, an antiproton appeared as well. For every electron, a positron. Each pair existed briefly, then annihilated back into light. Yet for reasons still unknown, this dance was slightly unbalanced. For every billion pairs that annihilated, one lonely particle of matter remained. That tiny asymmetry, 1 in a billion, is why anything exists at all. Had matter and antimatter been created in perfect symmetry, they would have destroyed each other completely, leaving only radiation. No stars, no planets, no life. But that minute imbalance tipped the universe toward structure. The excess matter, tiny though it was, became the foundation of galaxies and everything within them. This imbalance may have been set during the Planck epoch itself, a fingerprint left by the universe's earliest quantum fluctuations. Even in its infancy, creation leaned ever so slightly toward form. The Planck epoch is the ultimate boundary of our understanding. We can trace events confidently back to 10 to 36 seconds, to cosmic inflation, to the separation of forces, to the forming of the first particles. But before 10 to 43 seconds, the horizon of knowledge closes. Our theories diverge. Our language falters. And yet, that unseeable instant defines everything that followed. Every galaxy, every atom, every breath of cosmic radiation is a continuation of that original expansion. We are living in the long echo of the Planck time, a slow unfolding of what was once impossibly dense, impossibly small, impossibly bright. In that sense, the Planck epoch never truly ended. It lingers beneath the surface of reality, hidden in the geometry of space, in the constants of nature, in the hum of the cosmic microwave background. It is not a time long past, but a foundation still present, sustaining every second that has followed. To imagine the Planck epoch is to imagine silence so complete that even vibration is potential, not action. It is to stand before motion, before direction, before law. The universe in that instant is not a place, but a possibility, a field of pure potential energy condensed into the smallest imaginable scale. And yet, from that stillness comes the rhythm of everything, the vibration of strings, the oscillation of particles, the slow turning of galaxies all descend from that first quiver of possibility. Even thought, even consciousness is part of that unbroken chain of emergence from silence into form. The Planck epoch is the birthplace of being, not just physical being, but the very idea that something can exist rather than nothing. It is where the universe took its first breath and where physics learned to speak. We call this era where physics breaks, but perhaps it is more accurate to say where our understanding breaks, where the universe remains whole, but our equations fall silent. In that silence, there may be simplicity beyond our sight. Perhaps the universe was never paradoxical at all. Only our perspective makes it so. The Planck epoch reminds us that beginnings need not be understood to be real. They can simply be vast, quiet, unmeasured. A mystery held not for confusion, but for contemplation. In that contemplation lies calm, because everything we see, every atom, every galaxy, every pulse of light carries the imprint of that unity. Even now, billions of years later, you live within the unfolding of that first moment. Your heartbeat, your breath, your thoughts are the continuation of a rhythm that began when time itself began to move. From the Planck epoch, the universe expands into its next phase, the grand unification epoch, the electroweak epoch, and then the hadron epoch, where particles begin to coalesce into protons and neutrons. From quantum chaos, the first building blocks of matter appear. Gravity stabilizes, energy condenses, space smooths into a fabric capable of memory. Soon a remarkable event will occur. The universe will expand faster than the speed of light itself, stretching quantum ripples into the vast tapestry we observe today. That event is cosmic inflation, a sudden silent surge that set the stage for galaxies, clusters, and the great web of stars. For now rest on the threshold. The Planck epoch fades into memory, yet its echoes remain in every curve of space. The first breath of creation continues still slow, vast, and serene. From the silence of the Planck epoch, we step softly forward into a moment of unimaginable speed. The universe only a whisper, old still smaller than a grain of dust, still seething with raw potential, begins to expand. But not slowly, not gradually, not like the calm stretching we see today. In a fraction of a heartbeat, the universe grows from subatomic size to cosmic, from quantum to galactic in an instant. This is the era of cosmic inflation, a moment of expansion so swift and smooth that it reshaped everything that would follow. It is the bridge between the unknowable and the measurable, the moment when the storm of the Planck epoch gave way to the order we now observe in the stars. If the early universe were a breath, inflation was its first exhale, long, steady, unstoppable. We do not know precisely what caused this sudden burst, only that it happened between roughly 10, 36, 10, 36, 10, 36, and 10 to 32, 10, 32, 10, 32 seconds after the beginning so quickly that the numbers themselves blur into abstraction. At that instant, energy locked within a quantum field, the inflaton field, as physicists name it, began to release. Its potential energy acted as a kind of negative pressure repelling itself, forcing space to expand exponentially. Every tiny patch of the universe grew by a factor of at least 10 to 26 26, 1 to 26, perhaps much more. What had been microscopic became vast. What had been chaotic became smooth. And what had been quantum, ruled by uncertainty, stretched into the classical scales of cosmic geometry. The early turbulence of space-time, its quantum froth, was ironed flat by inflation's surge. The universe emerged even homogeneous and astonishingly simple. This was not an explosion in space, it was the rapid creation of space itself. Everywhere at once, instantly, quietly. Cosmic inflation did more than expand the universe. It solved several deep mysteries left behind by the Big Bang model alone. 3 in particular: flatness horizon and monopoles. The flatness problem asks why the universe today appears so geometrically balanced. According to Einstein's equations, even a tiny curvature in space would grow over time, leading to either collapse or runaway expansion. But the cosmos we observe is nearly perfectly flat. Inflation explains this by stretching space so vastly that any curvature became imperceptibly small, like the surface of a balloon appearing flat to an ant crawling upon it. The horizon problem asks why distant regions of the universe too far apart ever to have exchanged light or energy share the same temperature and density. Before inflation, there was not enough time for these regions to come into equilibrium. But if all those regions were once close together before inflation stretched them apart, their similarity makes perfect sense. Inflation unified the cosmos, then scattered it across immensity. The monopole problem refers to magnetic monopoles. hypothetical heavy particles predicted by early theories of unification. The Big Bang should have produced them in abundance, yet none are observed. Inflation solves this too. It diluted their density so dramatically that they effectively vanished from observable space. In this way, inflation smoothed, stretched, and simplified the newborn universe, transforming initial chaos into the calm geometry we now inhabit. To grasp the speed of this event is to approach the edge of comprehension. During inflation, the universe doubled in size not once, but perhaps 100 times or more, each doubling occurring in less than 10 to 36 seconds. A volume smaller than an atom expanded into something the size of a grapefruit and continued. After inflation ended, expansion slowed dramatically, but the momentum of that growth still echoes through the cosmos. The space between galaxies continues to stretch today, a quiet continuation of that first unimaginable rush. We sometimes call this the universe's growth spurt, but the phrase is too gentle. It was an awakening, a sudden immense transition from potential to form. The infant cosmos inhaled energy, and from that breath came everything. During inflation, quantum fluctuations, the smallest possible variations in energy, were also stretched to cosmic scales. Tiny ripples in the inflaton field, once confined to subatomic distances, became vast undulations across the universe. These ripples froze into the fabric of space-time as inflation ended, becoming slight over and under densities in matter. Billions of years later, those same fluctuations grew under gravity's pull, forming the filaments of galaxies and clusters we see today. Every structure from the smallest star to the largest supercluster traces its origin to these quantum tremors. Inflation thus connects the tiniest scale of reality with the largest. The micro became the macro. The quantum became the cosmic. The randomness of the smallest particles became the pattern of the heavens. If you look at the map of the cosmic microwave background, you are seeing those frozen ripples, the fingerprints of inflation still visible in the universe's oldest light. Even the faint modeling of temperature across the sky, a difference of only 1 part in 100,000, carries the imprint of those ancient quantum whispers. From uncertainty came order, from chaos structure, from silent song. As the inflaton field released its energy, it eventually reached a lower state, a valley in its potential landscape. When this happened, inflation ended. The energy that had driven expansion was converted into particles, radiation, and heat in a process known as reheating. The universe filled again with matter and light. The inflationary vacuum gave way to a hot, dense plasma, the same conditions that would later produce the light elements of Big Bang nucleosynthesis. In a sense, inflation did not replace the Big Bang. It prepared it, setting the initial conditions for everything that followed. What had been infinite stillness became radiant motion. Temperature surged, density rose, and time began to flow with rhythm. The universe, now vast and smooth, began its long cooling, a transition from expansion to evolution. The idea of inflation, though born from mathematics and necessity, finds its greatest support in observation. The uniformity of the cosmic microwave background, its nearly flat geometry, its tiny fluctuations, all confirm inflation's predictions. When satellites like COBE-WMAP and Planck mapped the CMB with increasing precision, they found the exact patterns inflationary theory foretold a nearly scale-invariant spectrum of temperature variations, random in phase, but coherent in amplitude, the statistical fingerprints of stretched quantum noise. Even the large-scale structure of galaxies, their distribution across the cosmic web, aligns with those same primordial ripples. Inflation is not just a theory of beginnings. It is a theory that continues to shape what we observe every night in the sky. If inflation happened once, could it happen again? Some versions of the theory suggest it never truly ends everywhere, that while it stopped in our region, it continues in others, endlessly birthing new universes beyond our cosmic horizon. This idea is known as eternal inflation. In this view, our universe is a single bubble in a vast cosmic foam, one pocket of calm among countless others, still inflating. Each bubble could have its own laws of physics, its own constants, perhaps even its own dimensions of space and time. Together, these form what physicists call the multiverse, an endless sea of possible realities, each a variation on a shared cosmic theme. Whether this vision is true or not, it carries a strange tranquility. It reminds us that what we see, our galaxies, our stars, our lives, may be one expression among infinite others, each born from the same silence, each expanding into its own unknown. Even infinity, it seems, grows. Inflation left the universe smooth, not only in structure, but in geometry. Across billions of light years, space is nearly flat, neither curving inward nor outward balanced to extraordinary precision. This uniformity allowed galaxies to form gradually without the distortions that would have followed from a warped cosmos. It also explains why the night sky looks the same in every direction. Inflation equalized the universe. It gave us cosmic serenity on the grandest scale. Even now, this calm persists. Galaxies cluster, stars burn, black holes form, yet on the largest scales the universe remains homogeneous. The expansion that began in those first fractions of a second still carries forward silently, continuously. In this way, inflation was not only the beginning of structure, it was the beginning of peace. A universe born in violence found equilibrium almost immediately. In its first second, it became smooth enough to last forever. Inflation also reveals a hidden beauty that time itself can emerge from symmetry breaking. When the universe was perfectly symmetrical, all forces unified, all energy undifferentiated, there was no meaningful change, no past, no future, only pure potential. As inflation began, symmetry broke. The inflaton field rolled, energy transformed space, expanded, and time acquired direction. Entropy. The measure of disorder began to rise. From that rise came the arrow of time, the reason events proceed forward, not backward. Thus, inflation did not only shape space, it sculpted time. It gave the universe a way to remember, a path to evolve, a future to unfold. Every second, since every moment of thought or motion, traces its lineage back to that first asymmetry, the falling away from stillness into becoming. When we look into deep space with telescopes like Hubble or James Webb, we see galaxies billions of light years away, ancient systems born when the universe was young. Their arrangement is not random. They form filaments and clusters separated by immense voids. These patterns, this cosmic web, are the grown forms of those tiny inflationary ripples. The slight overdensities became galaxies. The slight underdensities became voids. Inflation planted the seeds of all future structure distributed evenly, patiently, across a universe that had just begun to breathe. Each galaxy, each star, each planet, even the atoms in your blood can trace their ancestry to those early quantum fluctuations amplified by expansion, carried through cosmic history like the faint memory of a dream. It is tempting to imagine inflation as chaos, an explosive, uncontrolled event. But the mathematics and observations suggest something gentler. Though expansion was immense, it was smooth and silent. Everywhere the same unfolding with serene precision. The universe did not tear or collide, it blossomed. It did not roar outward, it drifted open. Inflation was not violence, but release, the relaxation of a field descending toward equilibrium, the easing of tension written into existence itself. In that sense, the earliest universe was not unlike meditation, expansion through letting go, energy becoming calm, potential becoming form. Nothing forced, everything unfolding according to its nature. Perhaps creation has always been like this, a quiet blooming from stillness. Cosmic inflation marks the beginning of the universe. We can see the boundary where speculation meets observation. It transformed the chaos of quantum foam into the harmony of galaxies, the heat of creation into the geometry of peace. And though it ended long ago, its echo remains. The universe still expands slower now, tempered by gravity, yet guided by the same hidden rhythm. Even now, billions of years later, the breath continues. Each second of your life unfolds within that same expansion. Every photon you see, every heartbeat you feel, occurs within a universe still stretching gently, endlessly. You are living in the long exhale that began when time first opened. Cosmic inflation is the story of how the universe learned to grow. But it is also the story of balance, how violence became stillness, how expansion became harmony, how existence learned to last. From here, the universe will cool further. Its forces will separate, and its particles will take on form. Protons and neutrons will arise binding into atoms. Matter and radiation will part ways, and the cosmos will begin to build itself slowly from the quiet aftermath of its own impossible birth. For now, let the idea rest in you like light. The same breath that carried galaxies outward carries you too softly, invisibly always. The breath of inflation slows now gently. The universe, vast and smooth, cools into its next rhythm, still expanding, but calmer, more defined. Space has stretched beyond imagination, and the wild heat of its birth has begun to settle into harmony. The first structures of physics, the rules that will govern every atom, every star, every galaxy, begin to take shape. What emerges now are the forces, the invisible threads that weave through everything that exists. They are the quiet architects of reality, holding particles together, shaping light, guiding the dance of matter and time. Before this era, during the Planck and inflationary epochs, all forces were one. A single unity, silent and complete. But as the universe expanded and cooled, that unity began to unfold, a slow, elegant unbraiding of the cosmos's hidden symmetry. It is here that diversity was born. Here, that structure began. Today, we know 4 fundamental forces that govern all physical interactions. Gravity, the shaper of stars and galaxies, the curvature of space and time itself. Electromagnetism, the force of light, electricity and magnetism, binding atoms and guiding radiation. The strong nuclear force, the powerful short-range bond that holds protons and neutrons together within atomic nuclei. The weak nuclear force, subtle and delicate, governing radioactive decay and the fusion processes that make stars shine. Every event in the universe, from the orbit of a moon to the flicker of a candle, arises from these 4. They are distinct now, but they were not always so. At the dawn of time, their differences were hidden in unity. As the universe cooled, that symmetry broke, and each force stepped forward with its own identity. What we experience today are the echoes of that separation. 4 voices that once sang as one. In the earliest moment, gravity was not special. It was simply part of the unified superforce that governed everything. But at about 10:43:10:10, 43:10 to 43 seconds, the Planck time, the first symmetry broke. Gravity separated from the others, its nature distinct. Unlike the other forces, gravity was not confined to the microscopic world. It stretched across space, infinite in reach, yet weakest in strength. Its language is curvature, not interaction, the bending of space-time, rather than the exchange of particles. We still do not fully understand gravity's quantum nature. We describe it through general relativity, a theory of geometry, and motion, not probability and uncertainty. And because of that, gravity remains the most mysterious of all, the quiet outlier among forces, older, slower, deeper. It shapes galaxies and black holes, planets and tides, yet it also whispers faintly through the fabric of the quantum world. It may have been the first to emerge, but it will likely be the last we understand. After gravity's departure, the universe continued to expand and cool. Between 10 to 43 TeV, 43 to 10, 43, and 10 to 36 10, 36, 10, 36 seconds. The remaining 3 forces, strong, weak, and electromagnetic, still existed as one. The grand unified force. In this epoch, energy was so immense that particles constantly exchanged identities, flickering between states, indifferent to distinctions that would later define them. The cosmos was fluid, its forces interchangeable, its matter not yet differentiated. Then, at about 10 to 36 as 10, 36, 10, 36 seconds, the symmetry broke again. The strong nuclear force, which binds quarks together inside protons and neutrons, separated from the electroweak interaction. The universe released a surge of latent energy, perhaps triggering cosmic inflation itself, the sudden expansion that smoothed and stretched everything. After this division, 2 great families of force remained: the strong force, governing the realm of nuclei, and the electro-weak force, still unified, governing light and decay together. For a brief span from 10 to 36 10, 36, 10, 36 to 10, 12, 10, 12, 10 to 12 seconds, the universe was ruled by the electro-weak force. In this age, light and matter were not yet distinct phenomena. Photons, W and Z bosons, and the Higgs field were woven into a single dynamic system. Then, as the universe cooled below 10, 15, 10, 15, and 15, Kelvin symmetry broke again. The Higgs field, an omnipresent energy field, acquired a non-zero value filling space like an invisible ocean. Through its interaction with particles, it granted them mass. Before this, matter had no weight, no resistance, no distinction. With the Higgs field, substance took shape. This event, called electroweak symmetry breaking, marked a quiet but profound transformation. Light and matter parted ways. The photon became the carrier of electromagnetism, massless and eternal. The W and Z bosons became heavy, confining the weak force to short ranges. In that separation, the universe became what we recognize: a world where energy and matter coexist, but behave differently. Each force speaks through particles' messengers that carry their influence across space. Physicists call them gauge bosons, and they form the connective tissue of reality. The photon carries electromagnetism, the light that fills space, the spark that moves between atoms. The gluons carry the strong force binding quarks into protons and neutrons through an unbreakable web of color charge. The W and Z bosons carry the weak force enabling transformations that create the light elements and power the hearts of stars. And though unconfirmed, the graviton, if it exists, would carry gravity itself, the messenger of curvature and attraction. These are the intermediaries of existence, silent travelers that give structure to matter and shape to time. Every photon in your room, every bond in your body, every wave of gravity passing through Earth tonight is a whisper from these unseen particles, the universe's quiet dialogue with itself. Physicists continue to search for a single framework that unites all four forces, a theory of everything, or TOE. Such a theory would describe both the geometry of space-time and the quantum fields of matter within one elegant expression. Two major candidates guide this search. String theory suggests that every particle is not a point, but a vibrating string of energy. Different vibrations correspond to different particles, just as musical notes arise from the same string played in varied ways. In this view, all forces are harmonies in one cosmic symphony, and gravity emerges naturally from their resonance. Loop. Quantum gravity, on the other hand, envisions space itself as discrete, woven from tiny loops of quantized geometry. Space-time, in this vision, is not continuous but granular, like a tapestry woven from invisible threads of energy. Both theories hint that the universe at its core may be musical, rhythmic, patterned, recursive. But as yet, no experiment has confirmed either. We stand on the shore of understanding, listening to waves we cannot yet see. At every step in the universe's evolution, symmetry gave way to complexity. In the beginning, there was perfect uniformity, all forces equal, all energies balanced. But as the cosmos cooled, those symmetries fractured. Physicists call this process spontaneous symmetry breaking, and it lies at the heart of creation. When balance breaks, difference is born. When symmetry falls away, diversity arises. From one came two, from two came four. From unity came contrast, and from contrast, structure. We owe everything from galaxies to gravity to this breaking of perfection. Even life itself, asymmetrical, imperfect changing, is part of that same unfolding. The universe learned to grow by learning to differentiate. It found meaning through imperfection. Though the early universe is long past, these four forces continue their quiet interplay everywhere. Gravity sculpts the vast. It gathers gas into stars, stars into galaxies, galaxies into clusters, binding them into filaments across the cosmic web. The strong force works in the intimate. It holds the nuclei of atoms together, overpowering electromagnetic repulsion, ensuring that matter remains stable. The weak force operates in the fleeting. It changes one particle into another, allowing stars to fuse hydrogen into helium, releasing the light that fills our skies. And electromagnetism bridges the scale between. It governs atoms' chemistry, electricity, and magnetism, the force that animates the material world and transmits every photon of light. Together, these forces weave the visible and the invisible into one seamless pattern. They do not compete. They coexist, each necessary for the others to make sense. Even now, billions of years after their separation, they work in harmony, as if still remembering the time when they were one. Among the four, gravity is the quietest and the most persistent. It shapes not through strength, but through endurance. While the strong and weak forces rule within atoms, gravity acts across galaxies, across time itself. It curves the paths of light. It gathers matter into spirals of fire. It slows the ticking of clocks in deep wells of space-time. We often call it weak because its pull between small objects is almost imperceptible. Yet it binds the universe together. It is the thread that connects everything with everything else. Gravity is patience, embodied the slow architecture of eternity. It never ceases, never releases, never rushes. It works quietly, invisibly, forever. As we search for unification, one truth becomes clear. The universe is not random. It is governed by laws that are consistent across all scales and all time. Every equation, every symmetry, every constant echoes the same underlying order. Even when physics appears divided, the deeper we look, the more we find patterns that connect. Electric and magnetic fields are two sides of the same coin. Space and time are aspects of one fabric. Mass and energy are interconvertible, bound by the equation E mc2 equals mc2. Perhaps unification is not something we must invent, but something already present, hidden in plain sight, waiting for us to see. In the same way that the universe unfolded from unity into diversity, we too are products of that unbraiding. The matter of our bodies formed through the interplay of these forces. Gravity gathers us to Earth. The strong and weak forces hold our atoms together and drive the reactions within every star that made our elements. Electromagnetism shapes every signal within our nerves, every flicker of thought, every heartbeat. To study the forces is to study ourselves, not metaphorically, but literally. We are made of their balance. We live because of their persistence. The universe is not separate from us. It continues through us. Every attempt to unify the forces is in essence an act of remembering, of returning to the universe's first moment of wholeness. Perhaps that is why physicists are drawn to this search with such devotion. To find the theory of everything is not merely to understand equations. It is to glimpse the simplicity from which all complexity flows. Maybe the universe in its quiet way is trying to remember itself through our curiosity, through our reaching minds. Maybe consciousness itself is the cosmos's way of feeling its own order. When we look for unification, we are not separate observers. We are participants in the same unfolding symmetry. We are the universe, thinking about its own forces, remembering softly the moment when all things were one. From the unity of forces, the universe descended into diversity. From that diversity, it built structure, matter, light, and life. Yet beneath that multiplicity, the old harmony remains a hum deep and patient, resonating in the background of everything that exists. Inflation gave the universe space. Unification gave it law. Together, they shaped the world. We see a world of balance between gravity's curve and light's straightness, between cohesion and expansion, between stillness and motion. Every atom, every star, every mind exists between those forces suspended in equilibrium. The cosmos breathes through their interplay. And as the universe continues to expand, those same forces continue their quiet dialogue, unseen, unending, ever the same, ever the. In the beginning they were one. Now they sing in harmony, four voices weaving one song. Gravity provides the rhythm, deep and steady. Electromagnetism shines as melody, bright and fluid. The strong force holds the chords of structure. The weak force gives motion and transformation. Together they create the music of existence, a cosmic harmony that stretches from the first instant to this very moment. And somewhere within that harmony, the memory of unity still lingers. A note sustained across all time, waiting to be heard again. The harmony of the four forces hums softly now. Gravity shapes the vast. The strong force binds the small. Light weaves through everything, and the weak force whispers change in quiet pulses of decay and rebirth. The music of the cosmos has found its rhythm steady, balanced, unbroken. But the universe is still light, still fire, still energy pure and radiant. Matter as we know it, solid, stable, tangible, has not yet taken form. And so begins the next transformation, the moment when light learns to rest, when energy folds into itself, when the immaterial becomes substance. This is the dawn of matter. The universe expanding and cooling crosses the threshold, where energy condenses into particles, and the architecture of existence begins. At the heart of this transformation lies a simple and profound idea. Energy and mass are one. Einstein captured it in an equation so elegant it feels inevitable. E and mc2e equals mcl2e is mc2. Energy and mass are not opposites. They are different expressions of the same reality. Energy can become matter. Matter can return to energy. The universe is a conversation between the two, endlessly exchanging form. During the first microseconds after the Big Bang, that conversation filled all of space. Particles and radiation transformed into one another with every collision, every interaction. A single photon, pure energy, could create a pair of particles, an electron, and its opposite, a positron. When they met again, they vanished back into light. Creation and annihilation, appearance and disappearance, a rhythm as old as time itself. The universe in these moments was a dance of transformation, not chaos, but balance. Every creation matched by an uncreation, every presence balanced by absence. In those first millionths of a second, the universe existed in a state unlike anything familiar, a glowing plasma of quarks and gluons. Quarks are the fundamental building blocks of protons and neutrons, while gluons are the carriers of the strong nuclear force holding quarks together. But at such extreme temperatures, trillions of degrees, quarks could not yet bind. The strong force, usually powerful, was overwhelmed by the heat. Everything flowed freely, a liquid of pure potential, dense and shimmering without distinction or structure. This was the quark-gluon plasma, a cosmic ocean where matter and energy were indistinguishable. It filled the universe completely smooth and radiant, as though all of creation were still molten, not yet cooled into form. In that seething fluid matter was already written, though not yet shaped. The universe was pregnant with possibility, a storm waiting to settle into calm. As it expanded, it cooled. Slowly, the strong force regained strength, drawing quarks together into trios, 2 up, 1 down a proton, 2 down, 1 up a neutron. In this quiet gathering, the first stable particles of matter appeared. They were the seeds of atoms, the anchors of everything that would ever exist. Around 1 microsecond after the Big Bang, quarks locked together permanently. The universe had cooled below 1 trillion degrees. Kelvin, still unimaginable heat, but enough for structure to hold. Protons and neutrons formed in abundance, each a tiny knot of energy stabilized by the strong force. For the first time, the cosmos contained things, entities that could persist through time rather than dissolve instantly back into radiation. This was not yet the matter we know, no atoms, no solids, no light we could see. But it was foundation. It was permanence in a sea of transformation. With this, the universe changed character. It became a place not only of motion, but of memory. Energy could now linger stored in mass, ready to build the scaffolding of stars. The universe, once pure radiance, began to carry form within itself. Energy was learning to rest. But balance demanded its due. For every particle of matter that formed a corresponding particle of antimatter appeared. They were perfect opposites, equal in mass, opposite in charge, reflections of one another. And when they met, they vanished together, releasing energy as light. In the early universe, this annihilation was constant. Matter and antimatter appeared and disappeared in blinding equilibrium, leaving the cosmos radiant and nearly empty. Yet something subtle, something extraordinary occurred. For reasons still not fully known, the balance was not perfect. For every billion pairs that destroyed one another, one single particle of matter remained unpaired. A tiny asymmetry, 1 part in a billion, tilted the scales of creation. That slight excess became everything. Every atom, every planet, every star, every living being that would ever breathe owes its existence to that minute imbalance in the earliest seconds of time. The universe did not choose symmetry. It chose survival. Perhaps even then it was learning that perfection cannot endure, that imbalance is the root of creation. As the seconds passed, the universe cooled further from trillions to billions of degrees. Radiation no longer dominated completely. Matter began to take the lead. Protons and neutrons drifted freely in a bright fog of photons and neutrinos. The expansion slowed but never stopped. Space unfolded gently like fabric relaxing after tension. In this calm, the particles that had formed could begin to interact in new ways. After about 1 second, neutrinos, the ghostly, nearly massless particles born from the weak force, decoupled from matter. They streamed freely into space, carrying information about the universe's first heartbeat. Even now, billions of years later, those same neutrinos continue to drift through us, through planets and stars, untouched, unchanged. They are the quiet witnesses of the universe's beginning. By 3 minutes, the temperature had fallen enough for protons and neutrons to fuse. Hydrogen became deuterium, deuterium became helium, and trace amounts of lithium formed the elements of Big Bang nucleosynthesis, the first chemistry of existence. Matter was no longer just mass. It had begun to combine. The first molecules of simplicity were born. For hundreds of thousands of years after nucleosynthesis, the universe remained opaque, filled with a dense plasma where light could not travel freely. Every photon collided endlessly with free electrons, scattering in every direction, unable to escape. It was a glowing fog, not yet clear, not yet open. Then, around 380,000 years after the beginning, the temperature dropped below 3,000 Kelvin. Electrons and nuclei combined to form neutral atoms. Hydrogen and helium took shape. With electrons bound, the fog cleared. Photons broke free and began their long, uninterrupted journey through space, the cosmic microwave background we observe today. The universe for the first time became transparent. Light was free to move. The cosmos entered its age of clarity, and with transparency came vision not only in the physical sense, but in the deeper sense that the universe could now reveal itself. It could begin to tell its story through light, through patterns, through the soft glow that still reaches us from every direction. Matter is not static. It is motion slowed into form. Even the most solid rock is composed of particles vibrating with invisible energy. Within each atom, the strong and electromagnetic forces balance in delicate tension protons and neutrons bound at the center electrons in quiet orbit. Space within atoms is mostly empty, yet it holds structure, resistance, and shape. At this scale, matter is a harmony of opposites, motion and stillness, attraction and repulsion, wave and particle. Every atom is both vibration and form. Every element is both light and shadow. To understand matter is to understand balance, the same balance that shaped the universe from its first second. Even now, matter is energy in pause. You, the chair, you sit upon the stars, beyond your window, all are condensed light resting in temporary form, waiting for release. Every particle carries within it the memory of its origin, a trace of that moment when energy slowed, when movement became mass. A proton is not solid in the way we imagine. It is a dance of quarks and gluons, ceaselessly exchanging energy. Its structure is fluid, its boundaries uncertain, its identity defined by motion. When we say matter exists, we mean that it resists change, but even that resistance is dynamic, alive with vibration. The stone is still yet inside it. The same forces that shaped the stars still hum. In truth, there is no such thing as complete rest. All matter vibrates with the residue of creation. Every atom carries the echo of that first transformation from light into form, from energy into being. And when matter returns to energy in the core of a star, in a burst of fusion, in the slow decay of an atom, that echo is released again, completing the cycle. Energy becomes matter. Matter becomes energy. The universe breathes in and out. If the early universe had expanded slightly faster, matter might never have formed the energy too diffuse for structure. If it had expanded slightly slower, everything would have collapsed back into itself. swallowed by gravity before atoms could arise. But balance prevailed. Expansion and attraction found equilibrium, creating a cosmos where energy could pause, where matter could gather, where galaxies could form. That balance is fragile yet enduring. Even now, billions of years later, it holds. The same ratio that allowed matter to condense into stars continues to shape the motion of galaxies across time. The universe was not fine-tuned by design, perhaps, but by harmony, by the natural unfolding of laws that emerged from simplicity into complexity, from unity into diversity. In that harmony, everything exists, precisely enough chaos for creation, precisely enough order for continuity. It may seem paradoxical that something so substantial as matter arises from emptiness, yet the vacuum of space is not empty. Even now, the quantum fields that fill the void shimmer with virtual particles, fleeting pairs that appear and vanish in an instant. From these fluctuations, energy emerges. Perhaps the early universe was not created from nothing, but from the restless potential of the vacuum itself, the natural tendency of the quantum field to fluctuate to create form. In this way, nothingness is not absence, but possibility. It is fertile, alive, capable of birthing entire worlds. And matter, the rocks, oceans, and living forms of the cosmos, is its most enduring expression. Every piece of matter is frozen light. When you look at a mountain or a planet or your own hand, you are seeing energy slowed to stillness. Matter holds time in its structure, the rhythm of vibration slowed to permanence. Stars reverse the process. They turn matter back into light, fusing hydrogen into helium, releasing the stored energy of creation once more. The photons born in those stellar hearts wander for millions of years before emerging shining across space, perhaps to fall on the surface of another world. Light becomes matter. Matter becomes light. It is the oldest exchange, the breath that connects everything. When you see the stars, you are seeing matter remembering what it once was. From energy to matter, from formlessness to form, the universe's transformation was not an act of chaos, but of grace. It did not roar into being. It unfolded, slowly, predictably, beautifully. Each law, each constant, each delicate ratio gave rise to the next. From light came motion. From motion came structure. From structure came memory. And now, across billions of years, those same atoms once forged in fire, once scattered through space, have gathered again into consciousness, into you. You are energy slowed into awareness, matter remembering itself, the universe observing its own transformation through your quiet gaze. Even now, as you breathe, the atoms in your body are part of that same rhythm, the continuous exchange between energy and form, between motion and stillness. You are not apart from that process. You are that process. The same light that filled the first second still glows within you. The same energy that once became matter continues its cycle endlessly, softly, forever. The story of creation has carried us far from nothingness to light, from energy to matter, from expansion to structure. Now the universe rests in its quiet continuation. Galaxies drift apart. Stars burn and fade. The forces that once roared in unity now hum in balance, steady and soft across the fabric of time. Yet one question still hovers like a gentle pulse beneath all understanding. If the Big Bang created everything, all energy, all matter, all time and space, then what caused the Big Bang itself? What stirred the silence before the first sound? What gave birth to the laws that allowed existence to begin? This is not a question of noise or explosion, but of origin of the spark that set symmetry in motion. And so, as we reach the quiet edge of the known, we look back at what has unfolded, tracing the rhythm of understanding that has led us here. Across the vastness of cosmic inquiry, 4 great discoveries uphold our understanding of the Big Bang. 4 pillars that keep the narrative of creation upright and steady. Cosmic expansion. The observation that galaxies recede from one another, their light stretched into red hues, revealing the universe's continuous growth. This was Edwin Hubble's gift to cosmology. The realization that space itself expands, carrying all matter with it like dots on an inflating balloon. Cosmic microwave background. CMB. The faint afterglow of the first light spread across every direction in the sky. It is the universe's memory still radiating the echo of that first fireproof that the cosmos once existed in a hot, dense state. Primordial nucleosynthesis. The formation of the lightest elements, hydrogen, helium, lithium, during the universe's first 20 minutes. Their abundances match predictions with astonishing precision, showing that the laws of physics have remained constant since the beginning. Cosmic evolution through redshift. The record of time written in light. The farther we look, the younger the universe appears, each galaxy a chapter in an ongoing story stretching backward toward the origin. These 4 pillars form the architecture of modern cosmology. Together, they reveal not only how the universe began, but also how it has evolved calmly, rhythmically, predictably. And yet, even with such clarity, the deepest mystery remains untouched. Why did it begin at all? The Big Bang describes what happened after time began, but not how time itself began. Our equations trace the universe backward, shrinking galaxies, compressing energy, heating radiation, until all existence converges into a single point of infinite density. A singularity. But mathematics falters there. Infinity is not a number. It is a symbol for ignorance. The singularity is a mirror that reflects our limits, not the universe's. We can describe what occurred after 10 to 43 10 cells, 43 10 to 43 seconds after the Planck time. But before that, our language breaks. Our physics dissolves. The canvas of space and time disappears, leaving no backdrop on which to draw causality. It is here that science meets silence. And in that silence, speculation becomes a kind of meditation. Some physicists believe that the universe did not begin as an explosion, but as a quantum fluctuation, a spontaneous event arising from the inherent uncertainty of the vacuum. Even in perfect emptiness, the quantum fields that permeate reality never rest completely. They shimmer with possibility, creating and destroying pairs of virtual particles in the blink of an instant. These ephemeral fluctuations may, under the right conditions, give rise to something more lasting. A bubble of space-time self-sustaining, expanding becoming. If this is true, then our universe may have arisen from nothing, but not a true nothing. Rather from a field of pure potential, a still ocean of probability, a sea of maybe. In this view, creation is not an act, but a transition, a natural unfolding from one state of being to another. The universe did not need an external cause. It was the inevitable consequence of the quantum laws that govern everything. From silence came fluctuation. From fluctuation came structure. From structure came light. The mystery deepens, but so does the calm. Another possibility woven from relativity and quantum mechanics suggests that the universe may be self-contained, a loop of cause and effect with no true beginning. In the 1980s, Stephen Hawking and James Hartle proposed the no-boundary model in which time behaves like a spatial dimension near the origin. Instead of a singularity, a sharp edge. The universe curves smoothly into itself like the surface of a sphere. A globe has no beginning point, no before or after the surface. It simply is. In this model, the universe has no boundary in time, no need for an external spark. It is finite but unbounded, complete unto itself. The cosmos becomes a self-arising system existing because it can, because the laws of physics permit it. In this way, existence may be its own justification, a quiet symmetry of being unfolding from timelessness. No beginning, no creation event. Just the universe existing softly without origin or end. Some theories imagine an even grander pattern that this universe is not the first, nor the only, but part of an eternal cycle. In the cyclic model, expansion and contraction alternate endlessly. A universe grows, cools, and thins until gravity draws it back inward, collapsing into a new seed, a new Big Bang, a new unfolding. The cosmos in this sense breathes, exhale, inhale, creation, dissolution, birth, rebirth. Each cycle erases the traces of the last but carries forward its fundamental laws, refined, renewed, timeless. Perhaps our Big Bang is simply one heartbeat in an infinite pulse of universes, each one giving rise to the next. If so, then time does not begin or end. It simply turns, and in that turning eternity finds its rhythm. Another path of thought extends from cosmic inflation, that rapid early expansion we traced before. In some versions of inflationary theory, the process never ends completely. While our region of space ceased inflating and cooled into stars and galaxies, other regions continue to expand endlessly, birthing new bubble universes beyond our horizon. This eternal inflation creates a multiverse, a vast, infinite field of universes, each with its own constants, dimensions, and histories. In one, gravity may be stronger. In another, stars may never form. In ours, the conditions happen to allow matter chemistry and life. Though impossible to observe directly, the idea carries poetic resonance. It suggests that creation was not a single act, but a continual flowering, each universe a petal in an infinite bloom. Perhaps there was never just one Big Bang, but countless beginnings, each unfolding in silence, unaware of the others, yet born from the same eternal field. The cosmos, then, is not a singular story, but an infinite library, and our universe is but one volume among endless shelves of existence. Even as we ponder beginnings, the universe continues its quiet motion outward. Galaxies drift apart, carried by the invisible push of dark energy, a mysterious pressure that accelerates expansion. we do not yet know what dark energy is. It may be a property of space itself, an energy inherent in the vacuum, or something deeper still, a hint of physics beyond what we know. Whatever its nature, it ensures that the universe will not collapse, at least not soon. Instead, expansion will continue perhaps forever. Galaxies will drift beyond one another's light, leaving only darkness, only isolation, only calm. Stars will fade, matter will decay, and the universe will grow quiet once more, returning perhaps to the stillness from which it came. In this way, the story circles back to its beginning, from energy to matter, from light to dark, from motion to stillness. The cosmos does not end. It rests. What caused the Big Bang? Perhaps. In the deepest sense, the question itself dissolves when time begins. Causality. The chain of before and after exists within time. If time itself began with the Big Bang, then there was no before, no realm in which a cause could act. Asking what came before time may be like asking what lies north of the North Pole. The direction loses meaning once the map ends. And yet, even knowing this, we ask not because we expect an answer, but because the asking connects us to the mystery. To wonder is to participate in the same creativity that brought the universe into being. Our curiosity is the universe's self-reflection, the echo of its first awakening. We ask, and in the asking, we become part of the unfolding. Perhaps the cause of the Big Bang is not hidden but woven into existence itself, not a separate event, but a condition of being. The universe is simply because it can be. The laws that allow its emergence are part of it, inseparable, eternal. In this view, the question transforms not what caused the Big Bang, but why is there something rather than nothing? And the only answer we may ever find is that nothingness itself desires to know itself, and so it becomes something. This may sound poetic, but physics too speaks in such language when equations end and imagination begins. At the limits of knowledge, science and wonder share the same voice. Creation is not confined to the first instant. It continues. Every second, stars form and die, elements combine and dissolve, energy changes form. The Big Bang was not a single event long ago. It is the ongoing expansion of being. You are part of that process. Every breath, every thought, every heartbeat is an act of transformation. Energy becoming motion, motion becoming heat, heat dispersing into the cosmic background. Even your smallest gesture participates in the same physics that shaped the early universe. The universe is still being created through you. And just as hydrogen once became helium, and helium became stars, so too do you transform what you are given light into life, life into meaning. We are small, yet our minds encompass galaxies. We are fragile, yet we carry within us the same elements forged in the first seconds of time. The iron in your blood was born in stars. The hydrogen in your body has never known rest since the Big Bang. To exist is to be connected to that entire story, not metaphorically, but literally. The atoms that compose your heart were once light, once plasma, once quantum vibration. They have traveled for billions of years to arrive here in this moment as you. And so when you wonder what caused the Big Bang, you are the question asking itself. The universe, through you, is seeking its own origin, looking backward through time with eyes made of the very stardust it once released. You are not separate from that beginning. You are its continuation. The Big Bang is not an explosion behind us, but a horizon that moves with us, a boundary between what is known and what remains unborn. Every discovery pushes that boundary outward, illuminating what once seemed unknowable. Cosmology is not a tale of final answers, but of deepening questions. Each theory, each observation refines the story, but never completes it. Like the expansion itself, our understanding stretches forever without end. And perhaps that is the beauty of it, that the universe never stops revealing itself, because revelation itself is its nature. Even as galaxies fade, even as stars cool, even as entropy spreads through every corner of space, something continues, the quiet persistence of being. Existence itself, infinite calm awake. In the end, the Big Bang is not a bang at all, but a becoming. Not a moment of noise, but the awakening of form. Not the beginning of something new, but the unfolding of what has always been possible. If the question remains what caused it, perhaps the truest answer is stillness. A stillness so complete that it became motion. A silence so deep that it began to hum. A nothing so perfect that it dreamed of something. And here we are, part of that dream, breathing, wondering, creating. The universe continues to expand softly, endlessly. Its beginning is everywhere, its cause woven into every atom, every light wave, every thought. It does not need a reason to exist, it simply is. And so are you.